thinking about the plumbing to do the parallelization, we're letting the runtime and the library that was designed to do this make the decisions about what's going to be best given our available system resources. It may run them all asynchronously, it may run them synchronously. So this is parallel invoke. This one works off of a delegate. And we saw that returning a func. It has a sibling, which is parallel for each, which does what you might expect. I've turned this around a little bit. Parallel for each. Now I'm supplying just the ratios, and then do resize returns a delegate itself now. We're no longer returning a func, we're returning an action. And this is just going to do a for each loop over each item in that collection and run that delegate against each one. And just like the previous example, this also implicitly waits. 2.03 seconds. And just for fun, I've run this a few times, the timestamps, and we can still see that we are definitely still writing out all these images. They're still just looking at different ways of approaching parallelizing the same problem. And those are great if you have a known set of data. So it's data-centric parallelization. Behind the scenes, that's using a set of new primitives, which, given the name of the library, the task parallel library, you can probably guess that we're going to use tasks. This looks pretty similar to the first TPL example. Ratio select, give myself delegate, do another select against that, passing that particular function so that we can kick off a task. Notice even the syntax around kicking off a task looks like starting a new thread. So they tried to keep it consistent. But the important thing to remember, when you say new thread, you're always going to get a new thread. It's always going to run on a new thread. When you're working with a task, it may or may not offload that and run it in parallel.
Can you manipulate that so it does if you care?
There are options that you can pass in, like not so much with the new when you're going directly with the tasks, but there's things like max degree of parallelization. So you can say don't run more than 4 at a time, those types of things.
It takes parallel options.
Right. Yeah, so there's a lot of things that are built in that allow you to control and manipulate the behavior of the TPL itself. Like threading, this works, but it's not recommended. You can do this, but rather than using new task, we actually want to use the task factory. This looks kind of familiar. Same basic pattern we just saw, but now we're saying task.factory.start new. You can liken this to the thread pool. You're working with you're letting the task parallel library decide how to create and allocate and schedule tasks versus saying, I'm going to do it myself. Otherwise, the interface is basically the same. Now, one thing I failed to point out on the previous example is task.waitAll. So we have ourselves an array of tasks. They all need to signal somehow when they're done, whereas they just keep going. So we can still block by saying wait all. There's a couple of different ways that we can wait. We can either wait on individual tasks. So the task has a way to wait. We're not getting a result off of these. So if we were calculating something asynchronously, waiting for a result, when you try to access the result property, that has an implicit wait in it, because I'm trying to get the value that was calculated, and it may not be done yet, but I can't move on until it is, so it implicitly waits. Again, I don't have to worry about any of those locking mechanisms. When we want to wait on more than one task, we need to use the static methods like wait all, or where some of these are, we've got wait any, or we can just hold off. There's a series of when methods, and I say when something finishes, then we can move on. So there's a lot of different ways that we can wait for our tasks to complete.
Sorry for the question. Is that smart? Meaning, is it safe to use in code that might itself do inside of a task? Or is that a problem?
It depends on what you're doing.
Okay.
Yeah, like anything else.
It's not magic.
Right. Yeah, and maybe you can get yourself into some ugly spots. So if you're waiting on this to finish, or depending on what your branching logic looks like, well, this thing's waiting to finish, but the parent task is waiting on child tasks to finish. There's all sorts of, there's still a lot of complexity. It masks a lot of complexity, but there's still a lot that we have to deal with. So, like any good programming question, the answer is it depends. Now here's where I think things get really cool. So remember our callback example. We had to pass a function, essentially, to the thread, in that case. So we're passing, this action is executing. When this is done, do the next thing. We had to pass functions around, and it worked, it did its job. It just made it a little bit more challenging to follow, especially when you're in the delegate, you're looking at the code. Let me jump back over there so we can talk about it a little bit better with some context. Let's go to very cool with callback. So I'm looking at do resize, and short of knowing the signature of do resize accepts some delegate, some operation to do when it completes, I don't really know what's going on. I look at do resize, oh, there's callback. What is callback going to do? I don't know. And why does this thing even need to know about that callback, right? The only reason it needs to know about the callback is that there's no other way necessarily to signal what to do when you're done. This is a common pattern in classic asynchronous programming. But in the task parallel library, we get this fantastic method called continue with. Fundamentally, conceptually, it's doing the same thing. So when you're done doing the primary work, the first bit of work, do this next bit of work. But I like this because now whatever runs as part of that task doesn't need to have any awareness whatsoever of what to do next. The task parallel library handles that. Maybe I want to give it additional data. Maybe I want to push more data into it. Maybe there's other dependencies. Any number of situations can arise where you don't necessarily want to be at the mercy of whatever signature you have for your process that you're running asynchronously. This gets us away from that because now, task factory, start new, do this thing. When you're done, do this other thing. There's some other interesting things going on in here though. With continue with, we're saying this particular piece of work, when you're done, do this other piece of work. Continue with gives us a new task. So we start off by creating a task. It goes and does the resize. When that resize is complete, we get a new task that's responsible for saving the file or writing it to the database, whatever the case may be. We're trying to prevent the calling thread, whatever is going on in this run method, from proceeding, we need to beware of which task we're waiting for, which group of tasks we're waiting for. Because if I return the task from here and waited on those, instead of waiting on the continuations, we would get into that same situation, the same scenario we had earlier, where we would leave scope in this console application, our program to terminate before we were finished writing, any number of things. So you need to be aware of which tasks are important for it to complete and which ones you can essentially fire and forget. And there's ways to relate tasks to one another. I don't go into it in this talk. The times I've needed to use it, I've been working with the task parallel library. I haven't really cared necessarily what what they call the antecedent task was, so I usually just care that it returns value.
So, I'm not really good with the lambda expressions over here. But,
Which one?
The fn function.
Mm-hmm.
So, are you saying we're running do resize when we?
Right. So so this select, the select on line 52, where we say do resize, that returns a new delegate.
Okay.
And so we're passing. I'm just calling that delegate
Got it.
fn.
Got it.
And so we're telling in this iteration, task factory start new running this particular delegate. When that task finishes, continue with saving the image.
What is the continue with method signature? Because I'm not seeing how. What does it take, an action delegate or something?
Yes, it's just like the task. It's the same structure. So there are tasks that return values, and there are tasks that don't. There's all sorts of guidance around that. In this particular one, start new, I'm using one that takes an action. And actually it's, no, this one I'm using one that takes a func with no particular input. And then the continue with
Return.
is taking an action that accepts a task as its parameter. So when we look at save image in this particular version, this function is what's being executed. So we've got a function, a method that's returning a function, right? But what is really important is that we need to work with that task of image, because that resulting image is the input to our save. We can see that in here. So our antecedent is task of image, and our image is antecedent result. So antecedent is the task that triggered this continuation. Ultimately, we're doing the same thing. We're just doing it in a little bit more expressive way. Run that one. 1.989. Still gaining the benefits of offloading the processing to different threads, because this one's saying, oh yeah, I have enough resources available, I can do this. So you'll notice that in the earlier examples, and so far any of the examples, I haven't had exception handling in it. You know why? Because exception handling in parallel programming really, really sucks. It's hard, and it just complicates things. It is far, far easier in the task parallel library. Let's go look at this code. Okay, so in my save image, line 34, throw new exception. Something has gone wrong in my processing, and I want to capture that. Let's say stop all future processing. Throw the exception. Like I said, in traditional asynchronous processing, thread-based, whatnot, it's really, really cumbersome. Task Parallel Library simplifies that significantly. Our run method has now been extended to follow a familiar pattern. Try catch. If this was in another thread, and Task Parallel Library wasn't managing this, it'd be much more complex. But here, all I have to do is traditional try catch. But what type am I handling? Aggregate exception. So this type was introduced specifically for the Task Parallel Library. When you have things running in parallel, how many exceptions can be thrown at any given time?
Whatever number you say, I bet I can beat it.
Exactly. You have no idea. You're no longer in a scenario where you have just one exception to handle. You can have 10 of your tasks fail. You can have, depending on what you're doing, 100 tasks fail. How do you manage that? Well, that's where the aggregate exception comes in. And what it essentially is a tree structure of all of the exceptions that were thrown. As I said, it's a tree structure. So familiar with the classic exception type. It has an inner exception property, so it gives you that whole tree of exceptions that led up to the one that you're actually handling. Aggregate exception extends the base exception with an inner exceptions property. And inside of that can be any number of additional exceptions, including additional aggregate exceptions. So if we have that scenario where tasks are spawning new tasks, which are spawning new tasks, all of those can have aggregate exceptions, which can roll up into an outer aggregate exception. And Microsoft said, handling these is better than doing traditional error handling on parallel programming, but trying to traverse that tree, finding all of the inner exceptions and finding all of the aggregate exceptions that could have more exceptions is really kind of ugly too. So there's a nice little flatten method. And what that does is it traverses the tree for you and it gives you a new exception with all of the tree just basically flattened. So all of those aggregate exceptions become additional exceptions in the inner exceptions property. So you don't have to traverse that entire hierarchy anymore. You just get them all in a nice flat structure.
I'm assuming then, because it's created as a tree and aggregate thrown at you, you have no real way of chronologically figuring out what happened first and when.
No, and how could you? Because you don't know when the tasks are actually executing, what order, which processor they're being put on, whether one of them follows a different execution path. So there's no real way of knowing anyway.
Which is why flatten
Right.
is perfectly fine.
Yeah, and then once you have that flattened structure, then you can iterate over those, find out the ones that you really care about, and handle those accordingly.
So wouldn't we just like give name to task? Like each time you're trying to invoke a new task, just give it a name?
You don't really do that in Task Parallel Library.
Okay.
Yeah.
Real quick question about, let's say, we're iterating through 200 of these things, so we're not gonna necessarily get 200 new threads immediately. There will be some batching of these things.
Yeah, it's going to figure out what the...
Will it do its best to stop midway, or will it go all the way through?
Some of that depends on the configuration, so any of the parallel options that you give, there's any number of things. Like if there's additional things in the chain, like you're trying to spawn new tasks, it would stop you, like you have an exception. But if there's another item doing a for each, for instance, the parallel for each.
Parallel for each will stop you.
Yeah, so it depends.
Do any of these techniques play well with any of the other techniques?
So generally, if you have a good case for kicking off a new thread specifically, there's nothing stopping you in here. The idea though is, Microsoft's guidance is if you're doing parallel programming in modern.NET, use the task parallel library. Let the task parallel library make the decisions for you about how to effectively use your system resources.
So I got my one big legacy thread that I throw off once in a while, and the rest of it can be under the new library.
Mm-hmm.
Okay.
Yep. Yeah, there's nothing stopping you from continuing to use the classic threading model.
Okay.
But new code should be using task parallel library.
And they're not going to conflict behind the scenes.
No, no. I could have these kick off new threads all day, but I prefer to, I personally also prefer to have the mechanisms that the task parallel library provides and the safety that that provides. And it gives a much more expressive way to create that parallelization. Okay. So now we're going to change gears a little bit. We're still going to continue the same theme, but I'm going to comment out a few things. We are going to start changing some types around. And let's do this. And that. And that. So I made a few changes here. Changes aren't particularly important necessarily, but I'll talk through them a little bit. So I've got a delegate type. I've essentially aliased. You guys familiar with this overload of the using directive? Instead of writing out action string string double array or func string string double array task, I shorthanded it using that way. The reason I've done that, notice the difference here. One is an action. What's an action? Ready? Action doesn't return anything, but a func does return something. What am I returning? Now returning a task. So that task we've been seeing for the past few examples has now become more front and center in these examples. Notice I prefixed this with async demo, or async demo runner is my alias instead of just demo runner. And now we're falling into the next group of examples. So I've got async await example. And I'm going to go to the definition on that. We've been following these same examples. And now we're introducing some keywords. Async and await. This is the current state of asynchronous programming in .NET. Async and await most of the things. They look like magic, but behind the scenes they're just syntactic sugar over the task parallel library. Await is a keyword that you'll find in async methods. Let's say, run this thing as a task. And the return type of that is a task, because it's essentially pushing it through, creating a new task, just like we saw in the previous examples. And then everything that comes after that expression, that's a .continue with. So it's wiring up the continuation for us, but it's doing it in a way that follows a more imperative structure. Just like lock wires up a monitor behind the scenes. Just like using wires up the call to dispose behind the scenes. Just like for each wires up get enumerator and move next. Async and await are just doing the same thing, but with the task parallel library. Run this. Wait a minute.
Yeah.
What happened? I said run these asynchronously, right? Resizing to 100, done resizing to 100, saving, done saving. That looks like the very first example we saw tonight, synchronously.
You have two ways.
Yep,
Don't wait till it's done.
telling it here, await. I don't want it to await there. Let's go with one that works a little bit better. Do that every time on this keyboard. That's something you gotta kind of watch out for when you're doing async and await. I didn't want to await every individual task. Right? I didn't want to wait for the I want to wait for the continuations, but I want to wait for each one of them to finish. I want them to still do their work off in parallel instead of just doing complex synchronous programming. So await, because they're spawning multiple tasks there, this code should look fairly familiar. We've already seen selecting a delegate. Well, now we're selecting to tasks. We're gonna, this when all, says when every one of the tasks finishes, everything in this array finishes, we're gonna wait on something. And we know we're waiting? So we have the await on all of that, because the result of when all is, guess what? Another task. So instead of saying, wait on all of these individually, one at a time, wait for the whole array of them to finish.
You should probably uncomment the dot wait in your program SES.
Yeah, probably.
Your timer's off too.
Yeah.
Your timer.
Yep, why? I was about to point that out.
It's not stopping.
Right, it still continues on with some pieces of this. So
program.
we've got resizing to 100 done, elapsed, oh crap, keep running. But it's still, the task parallel library itself is waiting because it has that mechanism in place.
It's much faster.
And I'm waiting for, yeah. So all of this stuff runs. Let's close that one down. And now for the final example of the evening. Async, await, cancellation, and exceptions. So bringing it all together. When you're dealing with threads, there are absolutely ways to handle stopping the processing. It's ugly. It's no fun to write. It's incredibly error prone. Task parallel library says cancellation token source. You can provide your own. It has one. Just create new cancellation token source and go to do resize. Task factory, start new. Has an overload that takes a cancellation token. The task parallel library is checking this token at each phase. And then my continuation, I'm just forcing an exception again. Just like we saw before, we can handle all the exceptions with a try catch. This time I'm also going to wait for task canceled exception. So the cancellation token, when we fire that, is going to throw out task canceled exception. Otherwise, I just fall back to generic error handling. So I'm going to run this thing as it is to start with. Let's look at our error. Fail,
Oh.
fail, fail, fail. Okay, great. Fail. Right, bottom. And yeah, I didn't fix the timer on this one. Let's. But we can have this cancellation token source I've got commented out variety of ways we can manage how it's canceling. Maybe we want to make sure that a particular task doesn't run too long, or any number of other factors. We want to trigger the cancellation on a button press, or who knows what, something else can signal it. For this, I'm going to follow the first example. I will say cancel after, and give it a time span. I'll say after a quarter second, stop running all the tasks, because I'm passing in the cancellation token to all of the tasks that the TPL creates. Oh, it says save, parameter is not valid. I haven't seen that one pop up. Oh, weird. That's weird. Oh, because it was canceled, it forwarded on, that's fine. But we see where the cancellation token was triggered, that time span elapsed, the timer behind the scenes based on that time span elapsed, task was canceled, processing stopped. We saw that other exception, because it continued on, the task was still trying to complete, because it checks at each phase. We can write additional code inside of our individual methods that are being executed in parallel to continue looking at the cancellation token source, do additional processing based on that. Generally, it's going to try to finish whatever it's doing, and then it just won't continue on when the token is triggered. So that's been a bit of a tour of asynchronous programming in .NET from 14, 15 years ago till today. And we've come a long way in terms of how we write asynchronous code, and it's especially important as our software needs to take more advantage of the scaling out or mobile devices that control how we interact with the user, whether they stay responsive for the user. When we're sharing environments with other software, it becomes increasingly important. So to go from having to work with these primitive threads all the way up to being able to say async and await is a huge improvement in simplification of a very complex problem. And the fact that things like async and await have found their way into JavaScript and gotten rid of things like the callback hell, that was the very first thing I ran into on a Node project. I welcome those changes. Seeing promises in JavaScript and how closely they conceptually relate to tasks and threads in .NET makes that mindset shift easier, having that kind of unification of these programming models, and when we have to work in things that are intrinsically asynchronous, makes that type of development so much simpler, and so I welcome that change. But thank you for your time. I appreciate you coming out, and I hope you learned something from this tonight.